Yeah, close enough. Morning, everyone. I'm tempted to say today's lecture is cancelled due to lack of demand. We have 134 students registered for the course last time I looked. So today we're barely 10% of the class. So yeah. And yes, this meme is related to AI, in case anybody is wondering. All right. I don't think there's anything specific I need to ask about course arrangements. I did post a blurb for one of the guest lectures, just a description of what it's going to be. I got that from Davina Govender from SARP. She'll be presenting on the 23rd of March. So that's the Monday after the test week. And she said, a bunch of her colleagues heard that she's going to be presenting and I also want to attend. It's kind of, The problem is it is compulsory. I will call the roll, which yes is how you say it. And I don't think there'll be enough space for a bunch of her colleagues to come and sit in when that happens. So yeah, this empty lecture hall, it's supposed to be full. Anyway, there was something else I wanted to say, which was, I did mention that there are a lot of other problems that can be solved using searching, and that I'm primarily using mapping problems because they're the easiest to visualize, but they're certainly not the only problems that can be solved in this way. And section 3.2.2 of the textbook gives some information, and on this page 88, they actually give a description of some of the kinds of problems that one can solve. So it's not just mapping problems. Yes, there is the traveling salesman problem, which is very much a mapping type problem, but also VLSI layout, robot navigation, assembly sequencing, protein design, etc. I mainly just wanted to make the point that yes, there are other applications to search algorithms. Please do not think we are limited purely to mapping tools. The second thing I wanted to speak about was the difference between it's too early in the morning, I'm forgetting the words. Where to go now? It's on the previous page. Admissibility. There we go. So, we spoke about admissible and consistent heuristics. Heuristics. So, this is then saying that if our heuristic is consistent or admissible, then we will get the best solution with an A-star search. Now, given that admissibility is a much weaker criterion, remember it just says that it doesn't overestimate the distance, why don't we just always use that? Why do we want to have a consistent heuristic, which is a much more tricky thing to prove? Because it's got that whole triangle inequality thing. And we'll see some examples later that just show that this is much more difficult to work through. The textbook actually has quite a long discussion about the fact that when you have a consistent heuristic, the first time you hit any state, it will be on the optimal path. So the whole process of trying to figure out which node should we retain and when do we terminate the search becomes a lot simpler when we're dealing with a consistent heuristic than when we're dealing with an admissible heuristic. It also makes the algorithm potentially quicker because we're only dealing with, well, the first time we see things, it's on the optimal path. So we can greatly simplify things like which node to replace and whatever, potentially reducing our time required to run the algorithm, not our time complexity, because that's related to the number of nodes we expand, but we can reduce the amount of time that we take to run it. So if you want a discussion about why we would actually want consistency instead of just going for admissibility, the textbook does have quite a nice discussion about that. So I just wanted to note that. So there are actually good reasons to use consistency, and at one point the textbook actually says there are some versions of A-star search that just say if you don't have a consistent heuristic, don't waste my time. So it sounds like, if we look at it just from the perspective of trying to evaluate the heuristic itself, it looks like a real pain in the neck, but its positive implications for the algorithm itself are so great that at times one doesn't even want to use anything else. Okay, so that's just something I needed to clarify from yesterday. Sorry, I should have muted that, shouldn't I? I don't know if you guys remember the TV series Frasier. And one day he's got someone in his studio with him because he's a radio personality. And he says, and this is the cough button for when I cough. It mutes me. And the guy's like, no, that's the reverb button. It's like, yes, all my listeners are familiar with my reverberating cough. Anyway, so one of the ways of measuring the success of an A-star search is looking at something called the effective branching factor. Effective branching factor. Now, we've already spoken about branching factor as one of the consequences of a problem. So this is the maximum number of nodes, maximum number of children that any node can have, the maximum number of successor states that any state can have. So if we say that the total number of states or the nodes generated by an A-star search is equal to n. N is just a number at this stage. There's no more significance to it than that. And we say that that n happens at a solution depth of d. So we now know how far down it is searched. What we can say is that n plus 1, remember this is the number of nodes generated, so we don't consider the root node because the root node is never generated. That's why we have the plus 1 over there. So we can say that this thing is equal to 1, because the first depth only has 1, plus b star to the power 1, plus b star squared, let's write it like this, plus b star to the power d. Okay, so we can treat it as if it was a breadth first search and just say at every level we just expand a certain number of nodes. Now if we go, so we literally just take the number of nodes we generated and work out the effective branching factor from that. So it's not that this is necessarily a real branching factor, it's an effective branching factor. The lower this effective branching factor, so smaller b's, or b star in this case, smaller values of that imply a better search. So in other words, if we have to search through a tree, an A star or a better heuristic will give us a smaller value of b. In the ideal case, b will tend to 1. Because if we have a branching factor of only 1, that's basically trivial. We're just searching one node on each depth. Now, we're generally not going to achieve that. I mean, the universe doesn't like engineers that much. So we're not going to achieve that. But if we could achieve that, that would be really nice. And so this is one way that we can measure the effectiveness of a heuristic, is does it lead to a very low branching factor? Does this heuristic give us a lower branching factor than that one? In that case, it's probably a better heuristic. There's another way the textbook also speaks about the depth improvement. So we go and we say, well, what is the complexity, the space complexity that one would have to consider? And well, we end up with an order of b to the d, because the branching factor to the depth. And then what we have is in this numerator, we have minus some, I think it's km they call it. And so if we compare it, the bigger we can make that km, in other words, the more we can reduce the complexity of the problem, again, that's how we get a better solution. So the main thing I just want you to do, to note here, is that we don't necessarily need to, I was trying to figure out why this has been bothering me. It's just dawned on me. That's supposed to be an E. Effective, not effective. All right, sorry. So we can use a branching factor, which is a relatively simple thing to calculate, at least using a computer. Or alternatively, we can use this other metric. But the point is there are metrics we can use to try to judge how good a heuristic is, with the effective branching factor being one of them. In general, a heuristic that gives a bigger answer is preferred, as long as it remains admissible and consistent. Okay, so the more accurate it is going to be, remember you can't overestimate the true cost. So the bigger the value returned, while still being admissible and or consistent, the bigger the value returned, the more accurate the estimate is going to be. All right. Another thing I forgot to say yesterday, I did mention that a consistent heuristic is also admissible. Let's have a quick look why. So a consistent heuristic says if we at a node and we estimate the cost to the goal, then this estimate must be smaller than the cost to go to any other goal, any other node, wherever it may be, plus its estimate. Okay. That includes going to the goal node plus its estimate. So we say that the triangle inequality has to apply. So this estimate needs to be less than or equal to the cost to go to a successor node plus the estimated cost to reach the goal. So the cost to go to the goal node is the cost to go to the goal node, and the estimated cost to reach the goal node from the goal node is 0. So this little thing over here explains why admissibility is a special case of consistency. I should perhaps mention, using the microphone today probably seems like a dumb thing to do. The problem is my throat gets really sore if I have to speak loud. So I know I'm probably deafening all of you. There is a reason, I promise. All right. So that's why a consistent heuristic is also admissible. However, if we just say this, it does not imply that that is also true. So that hopefully gives at least some hand-waving sort of example, some sense of why a consistent heuristic is also admissible, but an admissible heuristic is not necessarily consistent. Okay. All right, then the other thing is, great, so we can get a heuristic. How? It's all very good and well saying let's create a heuristic, but how do we actually go about creating heuristics? I mean, things like VLSI layout, that's chip layout. Great, but how do we create a heuristic that allows us to get a preferably consistent, if not admissible, estimate of what's happening? So there are some ways we can do this, sort of some stand ways. So we can have a relaxed problem. And what this is, we're just saying, we'll take the constraints of the problem and remove some of them. So I'll show some examples in a moment with sort of a map finding type of thing. The other one is the textbook uses the example of, I hope you guys played with these at some point in your life. You get those little things of 9 blocks and you've got one loose one and you have to move it around until you create a pattern. So a relaxed problem in this example is if we say that the block over there actually needs to be over there, then how many moves is it going to take it to get there at a bare minimum? 1, 2, 3, 4. Okay, so we add 4. And it actually turns out if you just go and take every block and say, assume the other blocks aren't in the way, and just move each block to where it is, that's the minimum we have to do. We can't do less than that. So we can then say, we'll add all of those up, and that turns out to be a nice heuristic for this problem. How have we achieved that? We've removed a constraint. We've removed the constraint that there are other blocks in the way and thereby get a nice heuristic. The other one that the textbook mentions for this problem, which is a worse heuristic, but is probably quicker to calculate, which becomes important in a moment, is just to say, if all the blocks have to be there, how many of them are in the wrong place? Why? We're simply saying if it's in the wrong place, we give it a score of 1 because it's going to take at least one move to move each block to the correct space. So that is, again, it's definitely an admissible heuristic because you can't have less moves than one move per block that's in the wrong space. So we can also create an estimate in that way. So that's creating a relaxed problem typically by removing constraints. Blah, 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 blah. The heuristic is consistent because of the triangle equality. And there are potentially algorithms that allow one to do this as well. So as with everything, if a problem's important enough, someone has made an algorithm for it. So yes, there are also algorithms for this. Another one we can look at is sub-problems. So we go and we say, well, we need to solve this overall problem, but in between that problem, we need to solve the following. So if we go back to this moving things around blocky thing problem, that heuristic that I said where we take, well, this block is over here and it actually needs to be over there, a sub-problem of that would be moving this to there. So we just take that number of steps. It's not the whole problem. We could also do it by just saying, well, let's include the other blocks, but let's just move them out of the way as necessary. So let's just solve the problem of getting this one block to the place it needs to be. That's a sub-problem. And we can often define them relatively good ways of doing it. In some cases, we can even set up databases if we've got this type of problem, this is how much it's going to cost to solve. So we can sort of pre-compute some of these things. The big problem here is that we can have shared moves or shared actions that need to be performed. So if we go and we say, well, we do a sub-problem for every block that is in the wrong place and just move the other blocks out of the way to get it there, we are going to have actions that are common to all of those solutions. So we're going to be counting them multiple times. Are we going to have an admissible heuristic? No, we're clearly going to overestimate the number of actions that we have to take because we're going to be counting certain actions multiple times. So we do need to be careful about that. And we need to be very careful to ensure that that doesn't happen. But again, we can use sub-problems to do it. And then, because this is an AI course, just learn one. So just give it to a machine learning system and let it figure out an admissible heuristic for you. All right. The benefit of this is brute force and ignorance. Well, okay, that's not really fair. The benefit of it is if we can't figure out as a human what a nice heuristic will be, we can potentially allow a machine learning system to do it. The trick is, how do you make sure that it is consistent and admissible? Because if you're using a black box system, you then need to check every single possible input in order to check the output. So we need to be a little bit careful. This is one of those cases where the fact that we can't be guaranteed that we will get the desired performance can be a problem. All right. Everybody happy with that? So these are some ways in which we can try to generate heuristics. I mean, I remember reading through this the first time and going, great, where do heuristics come from? So this is, I think, quite an important concept. Often it will be very problem specific, but these are just some general guidelines that one can use to try to get useful things. Right, then on to the examples I have been promising. So there is one here somewhere. There we go. So I pulled this out of the 2022 exam for no other reason than it is the quickest thing I found with a map on it. So there's nothing specific about this. But let's take a look at these cases and say, well, let's try to create, whoops, too far. Let's try to create a relaxed problem or a sub-problem using this map to see if we can't create a heuristic. So we need to start at A, get to Z. You'll notice that no matter what the problem looks like, there are all these consistent things. Yes, I do that intentionally in the hope that when people get to the exams, you're not sitting trying to figure out what I'm asking, you're spending your time solving the problem. All right. So if we want a heuristic for this, okay, let's take a relaxed problem as an example. So what is the distance from Q to Z? Well, it turns out it is pretty much 4.1. That 4.1 is the rounded off distance. So these are actually on a grid with the relevant spacings. So 4.1 is the distance. So that is just the Euclidean distance from the current node to the goal. So great, that one works for that. From there to there is, again, it's 5.1. It's just the Euclidean distance. What about O to Z? So if we can take a relaxed problem, the problem we have here is the constraints say we can only go to those three nodes. So in order to find the shortest distance from O, we would need to then consider that path, and the shorter of the two is 8.2. Okay, so it actually turns out to be that path. But the constraint we have here is that we can't go directly to the goal node, because that's not allowed. There isn't a road there, or for some other reason there's no way of getting there. However, that does not stop us saying, for our heuristic, we can just use the Euclidean distance. We know what the position of the goal node is. We know what the position of the current node is. So just work out the Euclidean distance between them. All right. Is this admissible? It must be. You can't overestimate the distance because you can't go shorter than a straight line between 2 points. So a Euclidean distance from any node makes an admissible heuristic. Is it a consistent heuristic? So that means that from this node to there, plus the estimated cost from there to there, let me use different colors. So let's go red. So that distance plus that estimated distance must be must be greater than the estimated distance from A to Z. Just purely due to geometry, that always has to be the case. I just want to emphasize, just by way of example, that we can also say that the distance from there to there plus the estimate to there must be greater than that estimate over there. So it's to any successor node, not only to the immediate successors. So yes, a Euclidean distance is both an admissible and a consistent heuristic. So this is a nice example of a way in which we remove constraints and end up with a really great heuristic. Except there are two multiplications, an addition, and a square root there's one addition, two multiplications, and square root going up in order of complexity every single time we want to do this. So if you want to be difficult, that is a reasonably costly computation in order to work out our heuristic. And the question is, the benefit we gain from the cost of computing that heuristic, will it pay off in the time we save in the search? That's actually something I forgot to mention. An important thing with heuristics is they mustn't be more complicated to determine than the actual problem itself. Because if they're more complicated than the problem, they're useless. They need to be simplified. So in other words, if we want to say, well, what is the estimated cost from A to Z? Well, perform a breadth first search and you will find the optimal solution. Is that a sensible way of doing it? No, of course not. Because the cost is going to be as much as actually solving the problem. So a Euclidean distance is maybe not the best way to do it. So let's see if we can look at a sub-problem. So let's have a look and say the horizontal axis over here is bigger than the vertical axis, so let's use the horizontal axis. And then let's say we are just going to make our heuristic the horizontal distance we need to move to get into the same column. Okay, so that's a sub-problem. It's part of the problem, but it's not the whole problem. Right, is it consistent? Is it admissible? That's the easy one. And the answer is it has to be admissible. No, it can't be admissible. Sorry, it must never overestimate the distance. But what happens if we have a node over here? Okay, so what is the distance to get from there to Z? It's 3. What is the horizontal distance to get from there to Z? Is 0. Okay, that's consistent. Can it ever work out? Okay, so it is admissible. Because we can never have a case where we overestimate the distance to the goal node. Okay, it always has to be less. So using either the horizontal distance or the vertical distance is part of the problem because we have to move horizontally and vertically. So if we just consider the horizontal distance, great. Now we have an admissible heuristic. Is it consistent? Okay. This is now, I'm trying to, actually, I don't know. So if I get this wrong, stop me and tell me. So if we start at this node, let's start at node O, for example. So from node O to Z is whatever that distance is, 1, 2, 3, 4, 5. So it's 5. Okay, to get to N costs us 4 and the estimate is still 5. So that clearly works if we're going purely vertically. If we're going purely horizontally, then we reduce the distance. It's still less than or equal to. So I can't think of a way off the top of my head in which we can not satisfy the triangle inequality. Because at best, the best case is we have nodes like this, and it will be equal every step of the way. But any vertical movement will mean that the cost of going to the next state plus the cost to the estimate will be greater, which is what we want. So that is also both a consistent and an admissible heuristic. So now we've taken a sub-problem. The benefit of that is no addition, no multiplications, no square root. So potentially that might be a better solution because it's an easier to compute heuristic. How about we want to try to be a little bit more accurate, and we're going to say we're going to choose either the horizontal distance or the vertical distance. Okay, now should we choose the bigger of the two or the smaller of the two? Let's choose the bigger of the two, because remember, a heuristic that gives us a bigger value, as long as it's admissible and consistent, is better. So from here, from node O to Z, we've got 5 that way and 3 that way. All right, is that admissible? Can we think of a case where the distance to get to Z will be less than the larger of the horizontal or the vertical distance? I can't think that that is physically possible. So that is definitely admissible. Is it consistent? That I'm not so sure. Let's see if we can think of a nice pathological case. So we want to make a movement I don't think we can, because you still have to move. You have to move that distance, but the problem is there a case where we can overestimate? No, we can. I know we can't overestimate because it's always going to be smaller. I don't know. Okay, one would have to go and sit and work through the geometry. You kind of see the idea that we're trying to say here is by removing constraints on the problem and by considering either simplified problems or sub-problems, we can create heuristics. We can then just check, are they admissible or inconsistent? And in this case, I think all of the heuristics we've considered may actually be both admissible and consistent. I'm just not sure about the last one, the maximum of the horizontal or vertical distance. But if the maximum of the horizontal or vertical distance doesn't work, we can use the minimum.
So, isn't it always impossible to overestimate the distance if you have like this grid structure? Because if you like eyeball it,
yes,
you can overestimate it like say 50, but if you know it's exactly 30.
I think you're right. I'm just hesitant to say yes because I don't know for sure. So I think you're right. I think it is impossible to overestimate the distance even if we use the larger of the horizontal or vertical. Another one we can use is the Manhattan distance. So the Manhattan distance is we just have to go along the grid. So now instead of saying we take the horizontal distance or the vertical distance or some maximum or minimum of them, let's take the horizontal distance plus the vertical distance. Okay, so from node O we go, what's that, 5 that way and 3 that way, so our estimated cost is 8. All right, that to there is the shortest, that's 8.2. We're actually fine with that one. From node N, we have to go 5 that way and 1 that way, so our estimated cost is 6, and our true distance, it's not even admissible. And the moment it's not admissible, it can't be heuristic either. So if it is heuristic, it is admissible. If it's not admissible, it's not heuristic. Just be careful, it's not consistent. So just be careful you know how those ones work. So using the sum of the horizontal and vertical distances, the Manhattan distance does not work because it fails at the admissibility step. Everybody happy with that idea? All right, let's then do another example. So this one is from 2024 semester test 1. So all I've done over here is not said how it's computed, I've just given a heuristic and I've asked, is this heuristic suitable for use by an AI star search? I like to try to ask questions like that, although in this case I see I did actually write, is the heuristic admissible or consistent? Apparently asking, is this heuristic suitable for an A star search is vague enough that people don't understand what I'm asking. Anyway. Okay, so we have those. So let's take a quick look through them. From Z to the goal node is a distance of 0, and we do not overestimate it. Surprise, surprise. From P to the goal node is a distance of 10. Our estimate is 8. We're fine. From O, where the heck is O? From O, the estimate is 1, and that distance is clearly more than 1, so we're fine. I didn't say it's a good heuristic. I just said, is it an admissible or consistent heuristic? From N, again, the distance is clearly more than 1. From M, the distance is 4, and it is 4. If it's equal, it's fine. It mustn't overestimate. The correct estimation is fine. From L, the distance is 2, that's clearly more than 2. From K, the distance, well, the estimate is 3, that's clearly more than 3. And from A, the estimate is 4, and that's clearly more than 4, whichever way we go. This one's quite an easy one because we can just sort of look like that. But bear in mind, we have to find the shortest path. Okay. So if the shortest path was that from K, then that's what we need to consider when comparing to the heuristic. This is maybe a bad example because it's a bit simple in that sense. If we go back here, we need to go and look at for O, we consider that path. Why? Because it's shorter than that path. So we do actually need to use the proper shortest path, not just the one that's on a straight line, the way I've drawn it. Okay, keep that in mind. These costs matter. So the cost between those two is the smallest, even though the cost of between those two looks like it's the same distance. It's just easier to fit it in a test paper this way. So just keep that in mind. So nothing overestimates. One of them's equal, that's fine. Nothing overestimates the distance, so we're good. All right, the question now, the actual question here. Where's my table? There it is. The actual question is the consistency. All right, so now we're going to say the estimate from, let's just take A. The estimate from A to Z is 4. Okay? So, if we go from A to any other node, so let's just take M for starters, the cost to go from A to M plus the estimated cost from M to the goal must be greater than or equal to 4. 9 is greater than 4, we're good. Right. This case, 5 is greater than 4, we're good anyway. We don't even need to worry about the heuristic because we're already greater than 4. This one, the cost to get from A to O is 3. That is less than 4. But the heuristic from O to the goal is 1, so they're equal, so it's fine. All right, does that make sense? So we don't have to worry about it as long as they're not greater than. So that one is fine. And we need to do this for absolutely everything. So we actually also need to do it from there to there, and the estimate to there has to be greater than 4, and from there to there to there to there to there to there, plus the estimate of the cost to get to the goal has to be greater than or equal to 4. Yes, sir?
So how did you choose the value we're comparing?
How do you choose the value?
That you're comparing with?
Oh, the cost from A to the goal.
So from the start to the end.
Yeah, so that's the triangle that's the triangle inequality. Let's do it for, where's something with a big cost? Let's do it for P. Okay, so from P, the estimate is 8. Okay, so firstly, the cost to make that move plus the estimated cost to the goal is greater than 8. So we're fine. The cost to go from P to A is 5, and the estimated cost from A is 4, is 9, so that's a total of 9, which is greater than the 8 estimate from P to the goal. So we're fine. All right. The estimated cost to go from P to A to N is 8, plus the estimated cost from O to the goal is 1. That is still greater than or equal to 8, so we're fine. And we have to keep doing this throughout the whole ruddy thing. The benefit we have here, though, is what we can do here is like I did with A. We can say the estimated cost from O to the goal is 1. So the moment we have traveled a distance more than 1, we can say we're fine. So from node O to the goal definitely satisfies the triangle inequality because the estimated cost from O is 1, and the cost from O to get to any of its neighbors, let alone its successors, is already more than 1. So regardless of what the heuristic is, we know that it is going to satisfy the triangle inequality. So, in the interests of saving time, and because I have the memorandum in front of me, let's consider node M, completely arbitrarily. Okay, so the estimated cost from M to the goal node is 4. So from M to the goal node is 4, so we satisfy the triangle inequality there. If we go from M to A, that's a cost of 9. That's already bigger than our 4, so we're fine. But that the 4 plus 9 plus 4 is 13. That's way bigger than 4. So let me just, where was it now? M. So from M to L, okay, so 1 is less than 4, and the cost from L to the goal node is 2. 1 plus 2 is 3, which is less than our 4 estimate from M. This heuristic is not consistent. Okay, please note, it is not consistent even if, in the test I only expected people to just consider sort of the one step, so to each of its successors. But even if the estimate to the goal node is greater, just for that case, it's not consistent. So even if there's a single one that shows it's not consistent, it's not consistent. Bear in mind, be with you in a sec, bear in mind you have to prove that something is true, you have to prove that it's true for every single case. To prove that it's not true for every single case, you only have to find one exception. Okay, so if you happen to, in the test, be lucky and just start with M, you've proved it doesn't work. Doesn't satisfy the triangle equality, we're done. If you choose the wrong one, you could be waiting a while, all right? So, as I say, the kind of hint I'd get is to say, well, you only really need to consider the cases where going from a node to the other ones is greater than that node's heuristic. Because if the cost of moving to another node is already greater than the heuristic, then the cost of moving there, plus the heuristic, which is greater than 0, has to be consistent. All right, question?
Just to clarify, so if one is inconsistent,
the whole problem is inconsistent. So the heuristic has to be consistent for every single possibility for it to be consistent. It only has to not be consistent for one possibility for that not to be true. So if it has to be true for all, proving it's true, not true for one proves it's not consistent. The same with admissibility. If there's one where the shortest path is shorter than the heuristic values, in other words, it's an overestimate, if there's one path, even if it's a path that would never be reached by the search, we don't know that when we're setting a problem up. The heuristic, the admissibility of the heuristic is a property of the heuristic, not of when we use the algorithm with it. So if there's one path, no matter which one it is, that doesn't satisfy either of those criterion, then the relevant criterion is not satisfied. And as I said, if we show that something's not admissible, it's immediately not consistent. All right, so that's actually quite helpful, I hope. All right, where? Oh, it is this picture. Okay. Now, having satisfied ourselves that this search, or that this thing is at least admissible, let's do an A* search. So we have to start at node A and we have to get to node Z, with an A* search. So we have to start at node A. All right. So the cost to get to A is 0. The estimated cost to get from A to the goal is 4. So let's just capture that. All right. Everybody happy with that? So, now I can't remember where the goal test is done. Nice. I haven't got that part of the memo with me. Goal test is done on expansion because we might generate a solution that's not the optimal one. If we had a consistent heuristic, the first time we generate the goal node, we can use it. If we do not have a consistent heuristic, which is the case here, then we're not guaranteed that the first time we generate the goal node, it'll be the solution. And that's why for A* search, in this case at least, we have to do the goal test on expansion. All right, so we're now going to expand node A. So is it a goal node? No, clearly not. It's the start node. So from A, we can go up, down. We can't go down. We can go left and right. So we can go up to M at a cost of 9. So let's go up to M at a cost of 9. 0 plus 9 is 9. We can go left to where? My picture. We can go left to O at a cost of 3. O at a cost of 3. And we can go right to P at a cost of 5. At a cost of 5. Right. We now need to work out what the estimated total cost to the goal is. If this was uniform cost search, this is what we do. Remember, we just take the cost up to where we're getting. That's our uninformed search. We've now got an informed search, so we have an estimate of the costs remaining to the goal. So from M, the estimate is 4. So 9 plus 4 is, our estimate is 13. For O, the estimate is 1. So 3 plus 1 is 4, and from P, the estimate is 8. So 5 plus 8 is 13. Okay, everybody happy with how I got that? What I would suggest you do, I've seen students do this, I've seen students doing this over the last few years, is put a little key over here and say this is expansion order, this is the cost, and this is the cost plus heuristic or something, just so that I know exactly what you're doing. I mean, in the pressure of a test, you might swap them around or something. I will try to take that into account. If you do this, it makes my job easier if you haven't followed exactly the same format, but you've done it correctly. And trust me, anything that makes your lecturer's job easier is very good when they're marking things. All right. So, which one do we choose to expand next? Which one has the lowest estimated total cost? So we're not using the lowest cost to reach the goals. That's uniform cost search. We're using the lowest estimated total cost, and at this stage, that is node O. So we choose to expand that one. Is O a goal node? No, it's not. So what can we do from O? From O, we can go up to L at a cost of 7. We can go up to L at a cost of 7. No. 3 plus 7 is 10. Remember, we want the cost to get to the node, not just the cost of the movement. From O, we can then go left to N at a cost of, I think it was 6. 6 plus 3 is 9, and right to A at a cost of 3. So that's A, and it's 3 plus 3 is 6. Now, have we seen A before? Yes, we definitely have. Was the previous time, we actually can't do it yet. We need to work out the total estimated cost. We don't just use this. You can actually, if you think about it, because the estimated cost to get from A to the goal node is 4. So this is going to be 4 bigger than that, and this is going to be 4 bigger than that, and wherever we get A, the value on the right here, the estimated total cost, is always going to be 4 bigger than the cost to reach it. So technically speaking, we could probably just say, when we see A again, we can already prune it because we know it cost us more to get to it, and we know the estimate is going to be the same. However, we're going to do it properly. So the estimated total cost there is 10. 10 is bigger than 4, therefore we prune this at step 2. All right. The cost to get to the goal node from L is 2, so 10 plus 2 is 12. And from N, the cost is 1. So 9 plus 1 is 10. That should be it. Everybody happy with that? Right. So which one do we expand next? We've got that one, that one, that one, and that one on our frontier. We expand the one with the lowest estimated total cost, which at this stage is N, with its lowest estimated cost of 10. So that is now expansion number 3. So, from N, we can go up and right. We can go up to K. Just see if I can clear all of this up. Yes. So we can go up to K with a cost of 4. So it's 9 plus 4 is 13. And we can go right to O at a cost of 6. So 9 plus 6 is 15. The estimated cost from O is 1, I can see it over there, so that's 16, and the estimated cost from K is 3, so that is then 16 as well. We have seen O before, and the last time we saw O, it had a lower estimated total cost, so we can then prune this at stage 3. Have we seen K before? Why do you say, oh, we haven't seen K before. All right, everybody still with me there? Right, then our frontier is now those nodes. Which one has the lowest estimated total cost? And the answer is L, because it has 12 versus 13, 13, and 16. So let's expand L. So from L, we can go. These are meant to be run by a machine, remember. They're not meant to be done by hand. All right, going through them by hand is just to make sure everyone's got the relevant concepts. So from L, we can't go up. We can go down to, where do we go down? We go down to O at a cost of 7, so that's 17. We can go left to K at a cost of 2, left to K at a cost of 2, and we can go right to somewhere. Right to M at a cost of 1. M, that's 11, sorry, this is supposed to be 12. Okay, so that's just the movements there. Then from O, our estimated cost is 1, so that's 18. From K, it's 3, so that's 15. And from M, I think it's 1. No, it's 4. So 11 plus 4 is 15. Have we seen O before? Yes, we have. And the total cost of the last time we saw O, or the O that we're storing, is lower, so we prune that at stage 4. Sorry, I should have put a 4 there. Have we seen K before? Yes, we have, over there. But in this case, the K we've just found has a lower estimated total cost of 15 versus the 16 we saw before. So we prune the one with the higher cost. See? Not consistent. All right. Because if it was consistent, the K we'd found originally would have been the one with the lowest cost. So here we can actually see that. So that one is pruned on number 4. So please note, we don't only prune nodes when they're expanded. We can sometimes prune a node when something else is expanded. I try to set problems up that have all of these little special cases in them. Not to catch you guys out, but to check that you actually understand. Have we seen M for Mike before? Yes, we have. 15 cost over there, 13 cost over there, so we prune this one at expansion 4. That is correct. Okay, so now our frontier is M, P, and K. Starting to resolve itself. Which one has the lowest? We've got 13, 13, and 15, so let's take one of the 13s. We'll start with the up, down, left, right when in doubt, so we can just go with this one first. So expansion number 5. From M, we can't go up, we can go down to A, so we go down to A. Ooh, it's terrible, it's supposed to be a D, not a 9. At a cost of 9 gives us 18. We can then go left to L at a cost of 1, left to L, which gives us 10, and we can go right to Z. To Z at a cost of 4. So that's 9 plus 4 is 13. Okay, so from A it's 4, so that's 22. The cost from L is 2, so that's 12. And the cost from Z is 0, so that's 13. Sorry, I know this is getting messy, but it's that size, so forgive me. Yes, sir?
So is there a way that you could print preloaded blocks on?
I do. Confused the hell out of people last year, but hopefully it won't this year. But yes, so what I did last year was I just printed a bunch of spots and then showed the first one, and then just printed a bunch of blocks, and you have to decide how you join them up. But yes, that not only makes it easier for you, it makes it easier for me as well. So yes, I will do that. Believe me. All right, so have we seen A before? Yes, we have, at a significantly lower cost, so we prune that at 5. Have we seen L before? Yes, at the same cost. So if we see things at the same cost, it doesn't really matter which one we prune. I'm going to say we retain the one that we created first, in this case. What the heck? 5, if something like this happens and you're not entirely sure which way to go, just tell me what you did. At the end of the day, I'm interested in why you did things less than I am in what you did. Yes?
So how would you go about pruning the nodes you've already expanded?
That's a jolly good point. I can't prune the node I've already expanded, so yes. I kind of have to prune the current one. Thank you. That actually helps more than I thought it would. You see, this is why I need questions, because I'm an idiot, and you guys are not. All right. Then, so that's number 5, Z we haven't seen before. Then, we now need to expand the last one. We've got a Z which is 13, a P which is 13, and that's it. Those are our two choices. We generated the P first. Yes?
So if all of our heuristic values were to be consistent, we would now stop here.
Yes, we could. We could. The way the A-star algorithm is written is that you have to test on expansion. So what I have had in the past is students say the heuristic is consistent, therefore I can stop now. That's fine. But you should actually be doing the goal test on expansion. So I'm assuming we're doing the goal test on expansion. In this case, we have to, because of the way the problem's set up. And should we expand this one or this one? It actually doesn't matter. So we could expand that one, I suppose, but expand the one we generated first. So this is now number 6. From P, we can go up to Z at a cost of 10. We can go up to Z, which gives us 15, which gives us 15 over there. And from P, we can go left to A at a cost of, I can't remember, 5. So 5 plus 5 is 10, and A is 4, so that's 14. So have we seen Z before? Yes, we have. It's over here. This one has a lower estimated total cost, so we prune this one. Stage 6. Have we seen A before? Yes, we have, up top there. This one has the higher cost, so we prune it there. Now, as keeps turning out in these problems, which is not the way I want it to work, but it is just the way it ends up working, we expand the node with the lowest cost, which, hey, guess what, is the goal node, because it's the only one left. So now we have our goal. So our solution is A up to M at a cost of 9, right to Z at a cost of 9 plus 4. To Z, and we go right there, and the total cost is then 13, and that is our solution. Is everybody happy with this? So it's any good computer algorithm, as is true with any good computer algorithm, it's painfully simple to work out by hand. But because it's painfully simple, it's also painfully simple for an idiotic machine to do. So the best algorithms tend to be very, very simple like this. We're not doing complicated things. It's just the repeated application and the blind, unthinking application that makes it a good computer algorithm. So hopefully that makes A-star search a little clearer and heuristics a bit clearer. And I will then see you on Monday. Have a good weekend.